Okay, welcome back. So we'll continue our discussion on that water quality issues and wastewater treatment and like water quality index and all that. So in the last video, if you remember, we were talking about this activated sludge process. So it's essentially it's an aerobic process where you will have, as you can see here, there is an aeration basin. This is an aeration basin. Aeration basin means that it's aerated. So we have oxygen being added. So we don't add oxygen, we add air. So this aerobic bacteria will be thriving here. They will use the fecal matter, the organic matter present there as a food source. So and that will create that will help degrade the organic matter. And while it will degrade the organic matter, since it's an oxygen process, CO2 will be released as well. So we add air and oxygen for radiation and mixing. If needed, we also add nutrients and alkalinity. It says if needed, alkalinity to control the pH, because microbial activity doesn't happen at very low pH and very high pH. It usually happens in the neutral pH range. So we need to keep it in the neutral pH range. So and then it taken to the secondary clarifier. So it's basically it's a settling tank where whatever is the organic matter, degraded organic matter gets heavier and they kind of settle down. And while they settle down, part of it will bring it back, because that has good microbes, so it brings back. That's why it is called activated sludge process, because the part of the sludge which is activated, when we say activated, it essentially means it has like good quantity of active microbes, so that can add in decomposition of organic matter in the aeration basin. And then it talks about the effluent is primary treatment is 20 to 30% of activated sludge. Mixture will enter the aeration tank. Microorganisms coated with sludge solid mixed with large quantity of air for about 4 to 8 hours. Sludge gets settled down in the secondary clarifier. So that's the one process. Another common process is this trickling filter. So trickling filter, as the name suggests, trickling. So it will kind of just go down, trickling down. So here it's an attached growth process. So it's we have and also it's also an aerobic process. It's an alternative secondary wastewater treatment. So we have media which it could be rock, could be slag, could be plastic material. So biomass actually grows on this media. So you have a pack of filter, essentially kind of a filter, where you have this biomass. This biomass will grow on this filter, and as the water as the wastewater passes through, so they will these microorganisms will use the wastewater as a food source, and in the process will degrade the wastewater. So it's an attached growth process, where the aeration is a suspended growth process. Attached means it is that microbes are actually it's on that either in this media, either rock, slag, plastic, or whatever material you use. So it's in that media. So water is flowing through that media. Where in aeration tank, microbes is also floating around, the organic matter is also floating around. So microbes will keep on eating them. So that's the major difference. So biomass growing on the media uses organic matter along with a portion of nitrogen and phosphorus to grow new microorganisms. So that's what happens. So you have this inlet coming up. This is your inlet coming into the system. Then it gets trickled around, and then finally the effluent coming out. Then we have oxidation ponds and aeration lagoons. So it's a suspended culture where it's an open flow through the like we also use oxidation pond, and we do have an oxidation pond here on campus as well for our sewage treatment plant. So you will have an open flow earthen basin which has a longer detention period. So usually after as part of the secondary treatment, after this activated sludge process or trickling filter, the effluent coming out, we just let it sit there in the oxidation pond, and it's an open flow through it's a longer detention period compared to other treatment units. It's aerobic, it could be facultative, it also could be anaerobic. So depending on where you are, so on top, since you have the oxygen interaction happening, so there will be an aerobic zone. Then as you go towards the bottom, things becomes anaerobic as well, and then in between you have the facultative, you have the sunlight, so you have algae, so you have CO2 being consumed as a part of photosynthesis, bacteria is present, and a lot of so this is essentially helps in removal of those organic matter. That is also happening over here. It is most suitable for country like India. So, in India you will see that oxidation pond is kind of used, its method is cheap and economical, and the problem is if it does creates problem in terms of mosquitoes breeding, and open flow could have some smell issues as well if not operated properly. So, that is what you see in terms of this oxidation pond. Then there are some anaerobic system where anaerobic and facultative stabilization pond, the deeper stabilization pond usually operating under action of anaerobic bacteria. There is also Imhoff tank, which is kind of improved version of our septic tank. Its incoming sewage is not allowed to get mixed with the sludge, and outgoing effluent is not allowed to carry with it large amount of organic load. So basically it helps, it lets the water, it gets treated in this tank, the wastewater gets treated and the clear water is allowed to go out and tries to control the amount of organic loading going out of the system. Then there are anaerobic contact process as well, where closed stir tank reactor, it says like a reactor effluent is settled in a sedimentation tank, its sludge is entrapped in the void spaces of the packing material, so things moving through, and then that again acts as a like it will use the organic matter as a food source and all that. There is anaerobic filter, there is a UASB reactor. So there are variety of treatment units are out there which you can use for anaerobic system as well. UASB is one of the most popular one. It's highly concentration of biomass, and again you have microbial sludge, and that's the wastewater kind of it's a off-flow anaerobic sludge blanket. That's the full form of UASB, off-flow anaerobic sludge blanket, and the waste kind of moves from the bottom to the top, and while it is moving from bottom to the top, whatever is the organic matter is there that gets consumed by this anaerobic set of bacteria. Septic tank, we know if you may have used septic tank especially in rural areas, and even in some urban areas still septic tank is used. So we have, it's essentially you have a retention period there, so waste degrades, and the clean water like the affluent from that gets moved to the other tank, and then finally it gets discharged through the soak pit and other stuff. So after these treatment systems, you try to let it settle. So another set of tanks which helps in terms of settling down. So it whatever is separates the suspended and biological solids, remove the settleable suspended solid as well. The concentrated impurities discharged from the bottom of tank is also known as the sludge. There are two end products, affluent as well as sludge, which is coming out of this, and both of them, affluent will go into the surface water. The sludge, it still contains some organic material. It can also have some pathogens, so it has to be treated before final disposal. So there are two types of sludge, the raw sludge and the secondary sludge. Raw sludge is what is you are getting in the primary treatment after the primary sedimentation, which we talked about in the previous video, the primary treatment part. That sludge coming out from that is called the raw sludge. It's a very high moisture, 95%, contains high putrescible material, so that it can be degraded. Then we have the secondary sludge, which is after the secondary treatment, after the secondary clarifier. So it does have putrescible matter, but it's less than compared to raw sludge. And the moisture content is again similar, 96 to 98%, so very high moisture. So those sludge, we do some biological treatment of those sludge because it does have some organic material. Then you let it settle down, then the final sludge coming out, you make it, you thicken that. As you can see in this bottom side here, sludge is allowed to thicken down, so you can use just let it be, it can be done either mechanically or it can be done by natural process. Let the sludge get dry. If you have a lot of space available, you can use sludge drying beds. Then you can even do further anaerobic digestion to get energy recovery. then you can do like take the dewatering and use that water back into the system. So different things, and then once it's dewatered, if it's sludge do have a good calorific value, so can be used as incineration as well. This energy, after energy recovery, the sludge coming out can be used for like agricultural purposes, fertilizer. So there are a variety of application that this sludge can be done. Incineration helps in volume reduction. There are different types of incineration plant where it is used. It does get incinerated with solid waste as well. It can be conveyed and stored for future use for as a fertilizers and other stuff. Sludge does have good nutrient value. So that kind of gives you a big picture idea about how wastewater is treated. So we try to cover that in like what maybe around 30, less than 20-25 minutes. So those of you who are civil engineering students, you will take a water and wastewater engineering course, and in that and like almost half a semester just goes on talking about wastewater, and half semester we talk about water. So that's a very exhaustive area, and even in fact in advanced level you will have an entire 1 semester course. Those who are in dual degree civil, if you go for environmental engineering in your like a specialization as part of dual degree, and then if you go for a master's or PhD in environmental area, you will have a whole course on wastewater. In fact, there are few courses on wastewater which kind of goes in more detail. Now talking about water, we treated wastewater or regular water, we are always worried about the quality of water, isn't it? The water quality. So that's always the cause of concern. So there is a simple way of expressing water quality is what is known as the water quality index. So it is defined as like composite influence of different water quality parameters on the overall quality of water. So you have different water quality parameters. So you look at the different water quality parameters, and then you try to have a composite number. So water quality index, in short form it is called WQI. So if you look at this WQI, it's to turn the complex water quality data is to easily understandable and useful value. So you don't want, see, if you talk about, when we talk about water quality, I will show you some of the parameters shortly. You will see there are metals there are inorganics, there could be organics, there is alkalinity, there is pH, there is so there are a variety of factors out there. So some of the important parameters has been taken, and that is converted into this information which is easily understandable and usable. Like if you look at your cell phone today, if you look at your mobile phone, and as soon as you get the mobile phone, if you just look at on the top, it will tell you what is the air quality index. So right now it says for Kharagpur area, it is set up, it gets my location. It says air quality index is 154. So similarly, we looked at the air quality the other day when we were looking at the air pollution problem. So air pollution issues. Similarly, we can have a water quality index. So water quality index gives an idea of how safe is my water, how clean is my water. So that's the whole concept. Because if you talk to somebody, to the layman, and tell them that, hey, my hardness is very high, alkalinity is high, there is arsenic there, there is a lead there, or there is this and there is that, and that guy will go crazy. He'll say, what are you talking about? Just tell me whether this water is safe enough for me to drink, or if it is bad, how bad it is. So they want a simple number. So that's why that's the kind of concept of this, that's the reason why we have this water quality index. So it is used for a specific, like if you have certain parameters, can be used for a specific information like industrial, municipal, irrigational, ecological, and it takes vast and complicated water quality data into a simple number that is easily understood by all. So that's the whole concept of this water quality index. Now there are water quality, we have there are a variety of parameters. So in terms of organoleptic and physical parameters, there are 6 of those, general parameters 25. We have 10 toxic parameter categories like heavy metals, mercury, arsenic, cadmium, nickel, we have pesticides like PAH, polycyclic aromatic hydrocarbons, PCB, I think it's bisphenol, PCBs, and then trihalomethanes, cyanides, chromium 6. Then we have radioactive parameters of alpha emitters and beta emitters, bacteriological, virological and biological water quality parameters. So, there are variety of parameters out there. So, but all these parameters are not equally important, as it says some parameters are more important than the others. So, all these parameters are not equally important. So, there are unit of measurements can be different, ranges of values are also different. So, we have too many parameters to monitor. So, it proves costly, time consuming and requires sophisticated lab. So, we try to bring it down to select finite parameters and monitor these water quality parameters against water quality against these parameters. So, what has been done is they have come up with a transform functions or curves, and they use them to transform the monitored volume into environmental common scale units. So, then we assign relative important values and obtain a weighted value to the parameters. Then we take the aggregate the parameter values, take the sum, average or geometric mean or combination of these, and use the maximum or you can use maximum operators or minimum operators, obtain sub indices and aggregate them together into finally getting this WQI. So, very simple way, you do not have to understand. Again, when you take this water and wastewater course, you will get more detailed information on this. But for now, for in general, since this is an environmental science course for all the discipline, all the graduating professionals, engineers, non-engineers, everybody here. So, here the major thing is that there are a set of parameters. So, we have taken the important parameters from there. We have done some mathematical, come up with a mathematical relationship. We have developed some transform functions and curves, and we have give some like a relative importance to these parameters. We put some, we took some weighted values, and then we took the sum, average, geometric mean, or the combination of that, and then we kind of put them in a form of water quality index. So, that is what it has been done. More details, of course, in the next courses, especially those relevant for certain discipline, you will be getting those information further. So, just just to give you some example, again this slide is not clearly visible over here, but in the class you will have a of this slide. So, basically I will just read some things very quickly from here. So, we are looking at we have a pH. So, we are looking at these are our pH, these are the different ranges for pH. Then we have this conductivity, turbidity, TDS, alkalinity, hardness, ammonia, nitrate, fluoride, iron, chloride, sulfate, fecal coliform, heavy metals, concentration ratio and pesticides. So, for all these there is a transform equation here. So, these transform equations have been developed which has been provided which is used in terms of water quality index. And then for each one of them we also have a final weight. So, weightage has been done, say for fecal coliform, chloride, fluoride, turbidity, nitrate, pH, TDS, hardness, iron, ammonia, nitrogen, alkalinity and all that. So, they have a weighted average has been done for all these different parameters based on their relative importance in terms of, that is what it says, relative importance values based on their relative importance in terms of water quality stuff. So, taking that we calculate, so as you can see over here, so these are the different water quality parameters. You can have all these parameters here, then you have monitored value in terms of you got those parameters, then you put them in the scale of 0 to 1, assign that relative value as you saw in the previous table, and then you get this weighted average. So, you get that individual for individual parameters, and then you take their sum together to get your sample, like how the water quality index can be calculated. So, in terms of some of the other like bacteriological, virological or biological requirement. So, for bacteriological requirement we do MPN test, the most probable number for getting the coliform bacteria. For virological you can do rotavirus, adenovirus, PCR, enterovirus. So, nowadays we all are we all have become little bit expert on virus with this coronavirus right now. So, this, you remember this PCR, that is what we have, what you say RT-PCR for our coronavirus as well. Then you are looking at the biological requirement, algae, Jew and the parasites, toxin and all those. So, all these different stuff for the biological stuff we need to we can have a look at there in terms of the water quality parameters from the biological angle. We also look at the suspended solid. So, these are basically will give us mostly inorganic material. So, it is a you can do the gravimetric in terms of milligrams per liter. Water is through the filter paper. So, how we get the suspended solid? You basically take the water, you take the dry weight of the filtered and then put it in the hot air. So, all the moisture will evaporate. Then you take hot air oven dried and take the final weight, whatever is the increase in weight, that gives you the total suspended solid, because you have taken the weight of the filter paper, you put the water through. So, whatever is suspended got into the filter paper, you dried the filter paper, took the weight again, the difference kind of gives you how much was the suspended solid, and then you can relate it to the volume of water. So, these are removed by gravity, filtration, flotation, the grid channels, primary sedimentation and all that we kind of talk about, those are used to remove those. We also do slow sand filter, rapid sand filter, those things are done again for the water treatment system. For water treatment we use slow sand and rapid sand filter to remove some of this suspended material. So, if you think about water treatment, I am not talking about wastewater, I am talking about water treatment. So, we get our raw water from either a lake or a river, or sometimes even from the groundwater. So, we need to make sure that things are treated there. So, it's we want to get rid of any of the suspended material and like dirts and other stuff. Then depending on the source, we have to go for disinfection and all that. If needed, we have to remove hardness, and so those are the things which is done in terms of getting the water treated. And before we put it into the water supply system, we have to treat that water further as well. Then colloidal solids, if you remove the turbidity, that's again you can remove the turbidity using those colloidal solid. So, this NTU is the it's a colloidal, like a it's a turbidity unit. So, it's essentially it tells you light passing through the sample is scattered, and the scattered light is measured by turbidity standard. JTU is also a white disk dipped uphill the depth at which it disappears. That is also measured in terms of turbidity as well. So, turbidity can be, again, turbidity is because of the suspended matter. So, suspended matter can be let it settle down, and if it gets difficult in settle down, we add some coagulants. So, flocculation is done to get those settleable material out. So, you can use some coagulant agent like alum, ferrous sulfates, ferrous sulfate, or you can then you make those colloids gets together, and then let it come down. So, and then zeta meter is used to measure the level of stability of the colloid particle. So, zeta potential is another thing, is also used for suspended nanoparticles and other things too. So, you can use slow sand filter, you can use by electrocoagulation, electroflocculation. So, those things are done as well. TDS is how much is dissolved there. So, it is measured again by gravimetric. So, same thing, you filter the water through, then you dry for dissolved solids at 180 degree centigrade, and you can also do it by the conductivity. TDS and the conductivity, they are they do follow each other, because TDS is caused because of your ions in solution. When things are in dissolved, they are basically ions in solutions, and ions in solution is the charged particle, they will be all there in solution, that causes conductivity. So, TDS, so if you plot, say if this is your TDS and this is the conductivity, you will see a nice correlation. So, more the TDS, more the conductivity. So, TDS can be removed by ion exchange, by membrane process, RO is used as well, RO or nanofiltration. distillation process, solar water, demineralization, dealkalinization, water softening. So, those are the things used for removal of TDS. Biological, say before you send the water for drinking purposes to the individual homes, you have to make sure that biologically it is safe. So, it should test negative for E. coli, that is very, very important. So, over 12 months 95% of the sample should test negative. So, that is also rest 5% should have MPN of less than 10 out of 100 ml. So, that is in terms of E. coli. So, in case of positive test result, what you do? You resample, confirm, and then immediately investigate to discover the source of contamination, and try to remediate that. So, the fecal matter and other stuff can cause MPN numbers. So, there are standard methods of how to do this MPN testing. All samples of water distribution system form should be free with all these different types of virus. Water should also be free from all these algae, geoplankton, parasite and toxin producing organisms. So, we keep a check on all these water quality parameters. So, if you need to treat it, if there is a bacterial problem, so how we review the disinfection? Disinfection can be done in chlorination, ozonation and UV radiation. So, those are the chlorination is very popular. Ozonation is also done, and UV radiation is what is done in the, if you look at your individual house, you have the scant water filter or AquaGuard or whatever brand you have, mostly they will use UV radiation for disinfection. Then for virus treatment for viruses, as you use again some virus is resistance to chlorine, but virus virus inactivation and redox is exponentially related. So, we kind of if you put a redox of around 650 megavolt, that make it most of the virus instantaneously inactivated. Now, treatment for biological requirement, again chlorination, but it could be ineffective. So, we again in terms of removal, flocculation and filtration, that does help. Membrane filtration, ultrafiltration, slow sand filtration, coagulation, that also proves effective in terms of removal of those biological matter. There are some heavy metals, sources of heavy metals are also present in the water. So, let us stop here and then we will start talking about this heavy metal in this subsequent video. So, we talked about this biological treatment, suspended material and all that, mostly in the water treatment side. In the previous video, we were talking about wastewater, kind of finished that wastewater part in the beginning part of this video. This video we started talking about water quality, starting from the water quality index, and we will continue this discussion in the next video, and then I think in the next video we will wrap it up. So, thank you and see you in the next video.